Let's look at this cable access network using the cable modem. Here, let's look at this configuration. This one is cable head end, and this is our house, and here we are using cable modem. This yellow one is cable modem, and this one is single coaxial cable, and many households are sharing this single cable. This is coaxial cable, and here this one is cable modem termination system, CMTS. Initially, the cable TV business was based on this coaxial cable and this house without this one. This cable modem was introduced later, around 1994, almost 25 or 6 years ago. And initially, ADL this modem was introduced first time. Later, cable modem. Around this mid-1990s, those are introduced. Thus later, this one is attached. Initially, this one was basic device, this one, except cable modem and the computer. And here, some schemes, as we learned already, multiple access schemes are being used. Here, frequency division multiplexing based on around 500 bandwidth, 500 megahertz bandwidth. For analog TV, this 6 megahertz bandwidth, each 6 megahertz bandwidth was used for each channel. And some channel was used for control signal, and this one is about that. Multiple 40 megabps downstream channel. This one is being used for downstream channel. And here, around 40 megabps can be implemented using this analog 6 megahertz channel. And multiple 30 megabps upstream channel. And this one is using multiple access scheme because all users contend for certain upstream channel time slots, and those will be explained in next slide. Here, let's look at this one. Internet frames, TV channels control transmitted downstream at different frequencies. Thus, we are using frequency division multiple access FDM, and also here, upstream internet frames, TV control, transmitted upstream at different frequencies in time slot. Also, this one is using different frequency division multiplexing and also time division multiplexing. Those are being used. Next slide is showing about that. Here, this one is explaining a little bit more about that multiple access scheme. This one is using DOCSIS. DOCSIS stands for Data over Cable Service Interface Spec. Here, FDM, frequency division multiple access. Those schemes are being used for downstream. And also TDM. Even for this upstream, this one is using some area of spectrum in terms of frequency spectrum. And also for upstream, this one is using TDM, a time division multiple access scheme. Some slots are assigned, some have contention, because many households are sharing this channel to access this one to ARP node. Before that, they should contend this mini slots containing mini slots request frames. Thus, each household, when this household wants to send some upstream data, then before that, this one is requesting this mini slots. Thus, this one is a mini slot request frame, and that is multiplexer scheme. And there may be some contention and some collision. If there is any collision, then later that is inferred that if that is not assigned, these mini slots, those are not assigned, then it is assumed that there is some contention and collision, then later it is requesting again. And if one household got the approval, and then this assigned mini slots that is containing cable modem upstream data frames from this house to send using this upstream channel. Okay, let's look at this one. FDM over upstream, downstream frequency channels, those are being used also. And the TDM, upstream, some slots assigned, some have contention. Downstream MAP frame, this one is MAP frame. Assigned upstream slots, and request for upstream slots. If this one is requesting, then that will be using this map frame and assigning upstream slots. Then using this one, the upstream traffic data frames will be sent. Request for upstream slots, transmitted random access in selected slots. Thus, to request this one, before that, using these mini slots, that will be requested. Thus, this one is the mini slot request frame. And many households are contending, thus there may be some collision. Then if the collision is inferred from not being assigned later, then it is doing this binary backup. Thus, this one is using FDMA and TDMA and multiplexer scheme, and those are all integrated in this single DOCSIS specification. Let's move. Okay, this one is summarizing of previous MAC protocols. We learned about channel partitioning by time, by frequency, or by code. This one is called the TDMA, multiplexers based on time division. This one is called the FDMA. This one is code division, multiplexers. Time division, frequency division, and code division. The analogous example is like using different languages in some public area, and so noise, even though this is so noise, different language can be understood by each one, like different language. That means that is like different code. This is similar example for this CDMA. Okay, random access. We learned about this. ALLOA first, and slotted ALLOA, CSMA, advanced one, CSMA CD. This is Ethernet. Also, for Wi-Fi, we are using collision avoidance, based on collision avoidance, CSMA. Carrier sensing, that is easy in some technologies. Wired one, that is easy, but it will be very hard in others. For example, wireless, for Wi-Fi. This one is being used in Ethernet, and also, as I mentioned, this one is being used for Wi-Fi. And also we learned about taking turns, this technology, polling from central site, and also token passing using some special bit pattern that is called a token. We can use this scheme. And the Bluetooth or fiber distributed data interface. Around until mid 1990s, this one was being used for backbone LAN. The speed is around that is 100 megabps, and at the time 10 megabits Ethernet using hub. Those are being used around until the mid 1990s, even until the late 1990s. At the time, this one was being used for backbone link, fiber distributed data interface using fiber data interface. But Ethernet technology, even gigabps speed is possible using Ethernet. Thus, this one is not being used anymore. And token link, IBM token link. IBM developed this one, and the 16 megabps speed was possible, and that was so successful. But the Ethernet scheme is very simple, and that is providing backward compatibility, and that can be manufactured in very low cost. There's Ethernet. That technology is being more proper. Ethernet technology is being more proliferated in the world, and that was more successful in the world comparing to the other technologies. In terms of the IEEE standard, those are 8.3, that is about Ethernet, and 8.4 same, also that is standardized by the IEEE, and that was token bus. And 5 is token link, that was token link. Among them, this one was final winner, and we are using until now, and also in the future we will use more advanced one in the gigahertz, gigabps, 80 or 100 gigabps. Those are being standardized. Okay, we learn about this subchapter LAN, and we learn about this addressing scheme and also address resolution protocol. This is address resolution protocol, ARP. We learn about this one. Okay, let's look at this MAC address. This address is called, in other words, physical address or MAC address. And this one is 32-bit IP address. And let's compare. Let's compare this MAC address, that is 48-bit address. After that, we learn about this ARP. To compare this MAC address to this 32-bit IP address, this is network layer address for interface. We learned in the network layer. And this is used for layer 3 forwarding. But this MAC address or LAN address or physical address or Ethernet address with many different names for this function is used locally to get frame from one interface to another physically connected interface. Same network in IP addressing sense. And this one is 48-bit MAC address. And this one is burned in network interface card, read-only memory. Also, sometimes it may be settable with software. For example, this one is hexadecimal format of that 6 byte or 48 bit, 6 byte, 48 bit Ethernet address. Each one is 1 byte, 2, 3, 4, 5, 6, 6 byte. Hexadecimal notation, 1 byte. Each one is 1 byte. Okay, let's move to the next. Okay, this one is about LAN addresses and the address resolution protocol. Each chapter 1 LAN has unique LAN address. Here, this one. That should be unique in the world. Also, this one should be unique in the world. Also, IP address, that should be unique in the world. That means public IP address that is unique in the world. Private IP address, it doesn't need to be unique in the world. Still, this one is explained about the LAN addresses. This MAC address, a location that is administered by IEEE. That is being standardized by IEEE, as I mentioned. IEEE 802.3, that is Ethernet. And manufacturer buys portion of MAC address space to assure uniqueness. And when they are manufacturing network interface card or Ethernet functionality in their embedded circuitry for Ethernet, then that will be used and assigned for that. Analogy is MAC address is like a social security number. In Korea, residential number, ID. And IP address is like postal address. You can differentiate between them depending upon your residence, when you are living, and when you are moving to other area, other city, then that address will be changed. IP address is like that. But your residential ID, that is almost permanent. Even though you are moving to other city, other area, still you are using same residential ID or same social security number in the United States. That is very similar like this MAC address. Thus MAC breadth address, that is providing portability. Thus we can move to other area. Still we can have the same address. We can move LAN card from one LAN to another. But if we are moving, then this IP address, IP hierarchy address, that is not portable. That should be configured again, depending upon the internet service provider's IP subnet address. Address depends on IP subnet to which node is attached. ARP, this one is explained about AR, address resolution protocol. Question is how to determine interface is MAC address. This one is Ethernet address, physical address, knowing its IP address. Thus each one should have this IP address and the MAC address. This one, IP address and MAC address. To send Ethernet frame, we need to find out that data link layer address, MAC address, that is called MAC address, or Ethernet address. Even though we have IP address, we should make our Ethernet frame using this one. We'll look at that format later. Thus, there should be some protocol to find out the matched IP address or matched MAC address. Thus, we are using ARP table. Each IP node, host or router on LAN has table. This one has table, also this one has table, also this one has ARP table, ARP table. Your computer in your house also they have. Also your notebook, they have ARP table. This ARP table has this mapping information, IP MAC address mapping for some LAN nodes, for example, IP address and MAC address, and other information that is time to live, just for the duration time in this buffer cache memory for address, and the time to live, time after which address mapping will be forgotten, and usually typically 20 minutes. That is 20 minutes. Okay. ARP protocol. Still we are learning about ARP protocol. Let's ARP protocol in the same LAN. That is more much more simpler than remote LAN configuration in the same LAN. How it is working. A wants to send the datagram to B. B's MAC address not in A's ARP table. Okay, instead of this one, let's look at the following one, this one. Let's look at this one first. Even though this one is using two different subnets, we'll try to focus on this. Okay, let's try to focus on this same LAN. First, let's try to focus on this first. Later, we'll expand to different subnet. Here, this one wants to send some frame, data link Ethernet frame. Then this one is using this one source address and two other IP address. Then this one is requiring this Ethernet address, and also to send to router in the same subnet. Then this one is requiring this one. But if it doesn't know that information, but it knows only this one, then ARP will resolve that address in the table to find out this MAC address. And the previous example, that is explained about that. Let's look at this one again. A wants to send datagram to B, then B's MAC address not in the ARP table, then that should be found. Thus, A broadcast ARP query packet containing B's IP address, because A knows B's IP address and but doesn't know that the MAC address for that. Then this one is sending this ARP query packet. Thus that will be broadcasted. Thus in the same net, in the same subnet, that broadcasting query packet will be arrived to each node. Destination MAC address for broadcasting, this one is MAC broadcasting address. Usually also in the IP address, even for 32-bit, all app, those are used for broadcasting. Here, 46-bit, if those are all 1, then that is broadcasting address. All nodes, when LAN receive ARP query, then B is there, then this one is receiving ARP packet and replies to A. It is B's MAC address. In this case, it is not using broadcasting packet. It is not using broadcasting destination MAC address. It is unicast, because it received already that query packet. Thus, it knows is sender's MAC address, because that is in their frame. as a source Ethernet address, source MAC address. That will be extracted and will be used for this reply. Then if A knows this MAC address, then it is caching, it is saving that IP to MAC address pair in its ARP table until information becomes old, until it is timing out. Substate, information that times out unless refreshed. If that detail value is 20 minutes, then after 20 minutes and it is not being used anymore, then it will be gone away. Here ARP is working in plug and play mode. Nodes create their ARP tables without any intervention from network administrator. Thus automatically it is configuring that ARP table. Okay, this one is the figure which we referred already, but this one is extending to other subnet. Okay, let's read this one first. This one is about addressing, routing to another LAN. This one is another LAN. And walks through send datagram from A to B via router R. Focus on addressing at IP and MAC layer frame. We have similar homework assignment. After solving that homework assignment, you can understand better. Thus, before solving that homework, please try to understand this one first. Assume A knows B's IP address. This one has IP address for that B. And assume A knows IP address of first hop router. First hop router is this one, gateway router. How? We are providing that information when we are computing to use internet. Or if we are using DHCP, then DHCP is configuring into that information initially. Assume A knows router's MAC address. How? Using DHCP, if it doesn't know that, then it can request using the ARP query packet, and it will get that. And that will be stored in the ARP table of this computer. That's MAC address of that routers. Then this one is explaining a little bit more into this frame, including that format field. A creates IP datagram with IP source A. Let's look at addressing routing to another LAN. This one is using Ethernet frame format, and some fields are filled with some value about this address and also IP address. Okay, let's follow this one. A creates IP datagram with IP source A and destination B. Here A, this one is B, as we learned in the previous slide. This one, creates the link layer frame to router's MAC address as destination address first. And frame contains A to B IP datagram. This one is sent IP source. This one is A's IP address. That is source IP address. And destination address is B's. This one source, this one. And that was down from the network layer to this Ethernet data link layer. Thus, this link layer's role is to make this Ethernet frame after encapsulation using this MAC source here, MAC source this one. This one is here, and MAC destination. MAC destination is in the same LAN, and to go out through this gateway, this one is for that. Thus, in the same link here, in the same LAN, from here to here, that Ethernet frame will be delivered. After that, this router will use that envelope. This is the envelope, and next one probably is explained here. This one is the next step. Frame sent from A to R. Here that is sent as we used that MAC source destination, and those are same. And that will be extracted after fill up that envelope. Thus this addresses, link address or MAC address, physical address, those are mainly to deliver properly to this router. That's it. After that, the contents of that Ethernet frame, this one is containing IP address, source and destination, A's IP address and B's IP address. That is not being changed. And this one is encapsulating again with other envelope, okay, like this. This router is doing that. And here, let's look at using this pen. And MAC source, this one is the MAC source because this one is sending, thus this one is sender source, and MAC destination. That is at the end of other side of this link here. Thus that can go through this same NAN, subnet, and arrive there. And inside these contents, the IP source address, IP destination address, those are same from the previous example. Okay, this one is explaining about that. Let's look at this one. R port datagram with IP source A, destination B. This router creates a link layer frame with B's MAC address, destination address, and frame contains A to B IP datagram. And finally, that will be arrived there. Router ports datagram with IP source. Router ports datagram with IP source A, destination B, and R, this R, creates a link layer frame with B's MAC address as destination, as we observed already in the previous slide. Frame contains A to B IP datagram. This same one, but this one is finalizing Ethernet frame transmission here. Okay, let's move to the next topic in this subchapter 6.4 lens. That is about Ethernet. Okay, this Ethernet, how that is being developed and evolved historically. This one is currently dominant wired LAN technology, most successful LAN technology. Compared to other token ring or token bus, still this one is surviving. This one is single chip, multiple speeds. For example, long time ago, Broadcom, that is IC manufacturer, that chip here, first widely used LAN technology. And this one is simpler, as we learned, and cheap, and cheaper than others. Kept up with the speed race until from this megabps range to this gigabps range. Still it is being evolved. Here original, this one is Matt Karp's Ethernet sketch. He was the PhD student, Harvard University, and he worked at MIT. Also he worked in the Palo Alto Research Center of Xerox PARC, Palo Alto Research Center of Xerox. Around the mid-1970s, he developed this one with other Intel and Digital Corporation together, 3 companies, including that Xerox. They developed this Ethernet technology. And Matt Karp, he went to the Hawaii and he used some Aloha scheme, and he got some idea using that Aloha scheme, and he developed this Ethernet technology. Original scheme, and he drew this Ethernet sketch mid-1970s, actually, 1970s. Here, this is the Ethernet cable called Ether, some media. This is terminator, original Ethernet, to terminate the electrical signal, both end as this termination device. That is called terminator. And to hook up this computer, we use this internet interface cable, and this one is transmitting and receiving, and this one is called transceiver. This is interface and the controller, Ethernet controller, and this is computer, PC or whatever, computer. And the other computer can be hooked up like this, using this interface and controller. And they are sharing this single resource, this multiplexer scheme, that this Ethernet, original Ethernet, that is being used. Okay, this one is the Ethernet's physical topology. First type, popular through mid-1990s, all nodes in same collision domain. Same collision domain means they can collide with each other. Star topology prevails today, and mid-1990s that was developed, this switch, late 1990s, and this one is doing this active switch like this. This is star topology, and each line is independent from each other, thus they are not in the same collision domain. Each spoke, this one, each spoke runs separate Ethernet protocol. Nodes do not collide with each other. That is excellent technology. In terms of the collision avoidance, they are not colliding. And in terms of performance, they can send at the same time. Thus performance-wise, that is being increased. Thus this switch is very important in this Ethernet success. Ethernet frame structure. This one is about the frame format of Ethernet. Sending adapter encapsulates IP datagram or other network layer protocol packet in Ethernet frame. This one is destination address, Ethernet address, 6 byte, 48 bit. And the source address, also this one is 6 byte. And this one is 2 byte type. And this one is data payload from data link, from network layer, that will be embedded here. IP, also TCP header, and some original actual data, they will be embedded here. And this one is mainly for error detection, cyclic redundancy check, as we learned. That is 32 bit, 4 byte. Here, this preamble, in front of this frame, this one is 7 byte first, and another 1 byte, that is 8 byte. 7 bytes is the pattern 10 10 10 like that, 7 times, like this, 1 2 and 7. And finally, this one is 8 byte, almost same except this one. This one is just in terms of the digital clock signal like that. 1 means this high voltage, 0 means this ground, and 1 0 it is like clock like this. How many times? Almost 63 times it is up and down like that, including them. 1 0 1 2 3 4 like that. And finally, this one is 63 64 here. This one is continuously 1 1. That means at the final, this one is like that. It is not going down like that. Then receiver will receive this signal, and after that, this destination meaningful address will be following. Thus, mainly this previous preamble that is being used for synchronization, like a clock. Used to synchronize the receiver, send the clock rays, because this one is apart from each other. This node, and this link, and that signal will be like that, this Ethernet through this Ethernet cable, or even wireless radio frequency signal. In our tightly coupled computer architecture, that oscillator clock can be used for other module or other device at the same time. That clock can be used. This clock from oscillator that will be used. But this is apart. They are apart. Thus, that clock cannot be used in terms of electrical characteristic, electrical signals characteristic. It is not possible. That will be distorted. Thus, instead of that, we are using this way. Okay, still this one is explaining about this Ethernet frame structure more. Addresses, as I explained, this one is explaining a little more. 6 bytes source destination MAC address. This one is explaining about this. If adapter receives frame due to matching destination address or due to broadcast address, for example, ARP packet, it passes data in frame to network layer protocol. Otherwise, adapter discards frame. Here, type is explained here. This is 2 byte. This one is mainly for demultiplexing. Like the previous network layer, upper layer protocol, one field is about upper layer protocol. Or in the transport layer, like the port number, there's for demultiplexing, that capability, that functionality, this one may be used, 2 byte. And also, that is being used for ARP, for example. In that case, the 2 byte is like this, 0806. That is for ARP frame. This one is anyhow. This one is indicating higher layer protocol, mostly IP, but others possible. For example, Nobel and Apple Talk, and they have standardized some code for that. And this CRC, as we learned already, cyclic redundancy check at receiver, and then maybe calculated again, and this one will be sent after calculation when this one is being sent, and that CRC in the receiver, that will be compared whether that is equal or not. If this one they are equal, then that is error free, and this one is not equal, then corrupted. Then this Ethernet frame will be thrown away. Error detected, the frame is dropped, then that should be retransmitted. Okay, this one is explaining about the Ethernet a little bit more, about the reliability and some connection. Ethernet is actually unreliable and connectionless. Connectionless means no handshaking between sending and receiving network interface cards, Ethernet cards. And this Ethernet is unreliable. That means receiving network interface card doesn't send acknowledge or not acknowledge to sending network interface card. Data in dropped frames recovered only if initial sender uses higher layer reliable data transfer, for example TCP. Otherwise, dropped data lost. Thus, Ethernet or this MAC layer is not providing reliable transmission. Ethernet's MAC protocol, that is unslotted CSMA CD with binary backup technology, as we learned already. Okay, let's wrap up here, and we'll continue from this slide later in next lecture.